You search for cheap flights, and the results also show affordable airfare and budget travel deals, words you never typed, or Spotify recommends a song you love even though it shares no words in common with the songs you played, or your AI chatbot somehow understands that happy and joyful mean the same thing. None of this is magic. Behind all of it is one idea: embeddings. An embedding is how an AI converts a word, a sentence, or an entire document into a list of numbers that captures its meaning. In this lesson, you will learn exactly what that means, why it is the foundation of modern AI applications, and how to use it in your own code. Here is what we will cover in this lesson. First, why computers need embeddings, the core problem with words. Then, how embeddings work, walking through the full pipeline from text to numbers. Next, similar meanings, similar numbers, the single most important property of embeddings. After that, keyword versus semantic search, and what changes when you use embeddings. Finally, generating and comparing embeddings with live Python code. Let us get started. A computer has no idea what the word dog means. It sees a sequence of characters, which is just a pattern of bytes, completely meaningless without context. The word dog and the word cat look completely different as text, yet any human instantly knows they are closely related. For an AI to understand language, it needs a way to represent words as numbers so that words with similar meanings produce similar numbers. Think about GPS coordinates. London is at 51.5, 0.1. Paris is at 48.8, 2.3. They are close together as numbers because they are close on the map. Tokyo is at 35.7, 139.7. Very different numbers, very far away. You can calculate distance between cities just by comparing those coordinates. Embeddings do exactly this for meaning. The breakthrough was that meaning can be encoded as a point in a mathematical space where distance represents how different two meanings are. Dog and cat get coordinates that are close together. Dog and skyscraper get coordinates that are far apart. The numbers encode the relationship. Here is the full pipeline. Raw text enters first: a sentence, a paragraph, a search query, anything written in natural language. The computer still has no idea what it means at this stage, it is just characters. Next, the embedding model, a neural network trained on enormous amounts of text to learn which words and phrases tend to appear in similar contexts. It reads the raw text and converts it into a list of numbers that captures the meaning. The output is a number vector, typically a list of 1000 to 1500 numbers, each a small decimal. Every piece of text gets its own unique vector, its address in meaning space. Compare vectors is where the power appears. Two vectors can be compared mathematically in microseconds. If the numbers are similar, the meanings are similar. If the numbers are very different, the meanings are unrelated. Finally, relevant results are what the user sees. Content ranked by how close its vector is to the query's vector, not by matching exact words, but by matching meaning. The single most important property of embeddings is this: words or sentences with similar meanings produce vectors that are close together in number space. Happy and joyful produce very similar vectors, their numbers are almost the same. Dog is closer to cat than to airplane. The vectors reflect the real world relationship between these things. Most powerfully, I am hungry and I need food produce nearly identical vectors even though they share no words. The model learned they mean the same thing. Think of a color wheel. Red is 255.00 and orange is 255.165.0. Their RGB values are close. Blue is far away at 00255. You measure how similar two colors are just by how close their numbers are. Embeddings work identically, but instead of three numbers for color, you get 1500 numbers for meaning. Words that live in similar contexts end up with similar numbers. This property, similarity based on meaning rather than the exact words used, is the foundation of every modern search engine, every recommendation system, and every AI that answers questions about your documents. Let us compare the old approach with the new one. Keyword search is how the internet worked for its first decade. It is simple and fast but completely literal. It looks for the exact words you typed, nothing more, nothing less. A tiny variation in wording loses the result. Search for car and results containing automobile or vehicle are invisible even though they mean the same thing. Miss a synonym and you miss the result. The computer has no concept of meaning at all. Semantic search uses embeddings to bridge the gap between the words you used and the meaning you intended. Because similar meanings produce similar vectors, the search does not care whether you wrote car or automobile. They produce similar enough vectors that the relevant results surface either way. I need food finds recipes even if no result contains the word food. It works across synonyms, paraphrases, and even different languages. This shift from matching characters to matching meaning is one of the most important advances in how computers handle language, and it is powered entirely by embeddings. Let us write the code. We start by calling the embedding API client.embeddings.create with two required fields, the model name and the text we want to embed. We are using text embedding 3 small, which is OpenAI's efficient embedding model, fast, affordable, and produces a strong 1536 dimensional vector for any input text. Think of it like the chat API, but instead of generating a reply, it hands back a list of numbers that represent the meaning of your input. Next, the vector is just a Python list. Response.data.embedding gives us a plain Python list of floating point numbers. No special data type, no magic. You can loop over it, store it in a database, compare it to another list. The entire meaning of your sentence lives in this list. Finally, let us print and see 1536 numbers for one sentence. Each number is a small decimal. On their own, they mean nothing to a human, but run the same model on a different sentence and you will get another list of 1536 numbers. If the meanings are similar, the lists will look similar. That is the engine behind semantic search. Now let us measure meaning with a number. The embed helper wraps the API call so that one line to get any vector, any text in, 1536 numbers out. We call it 3 times, once for I love dogs, once for I adore puppies, once for the stock market crashed today. 3 sentences, 3 vectors, each a unique address in meaning space. Next, the similarity function answers how close are 2 vectors. It uses cosine similarity, which produces a score between zero point 0.0 and 1.0. You do not need to understand the math at all. Just remember, close to 1.0 means very similar meanings. Close to zero point 0.0 means almost nothing in common. That is the entire scale. Now look at the result, meaning captured in a single number. Dogs and puppies score 0.9281, nearly identical because they describe the same animal in the same emotional tone. Dogs and the stock market score 0.089, almost no shared meaning at all. The model figured this out entirely from patterns in text during training. No dictionary, no synonym list, no handwritten rules, just embeddings, and the idea that meaning can be encoded as a point in a mathematical space. Let us bring it all together. An embedding is a list of numbers that represents the meaning of a word, sentence, or document. It is the bridge between human language and the mathematics a computer can work with. The most important property, similar meanings produce similar numbers. Dog and cat are close in embedding space. Dog and skyscraper are far apart, exactly like GPS coordinates capture physical closeness. Computers could only match exact words before embeddings existed. Semantic search, which finds results by meaning rather than by the exact words typed, is only possible because of the embedding idea. Every modern AI product that handles language uses embeddings at its core. Search engines, recommendation systems, document question answering, chatbot memory. You can generate embeddings with one API call and measure semantic similarity with cosine similarity, a score from zero point 0.0 to 1.0 that tells you instantly how related two pieces of text are. Open your code editor right now and run both code examples from this lesson. Try sentences in different languages, try paraphrases, try opposites. In the next lesson, we build retrieval augmented generation on top of exactly this foundation.